Alrighty, so let's finish up Unit 6, Molecular Compounds. Alright, so we have a bond that is made between two atoms, and it's a sharing of two electrons. Well, a lot of times those electrons are shared very evenly, and sometimes they're not. Now, we talked about this a couple units ago, the electronegativity of an atom. Electronegativity is a number which is a measure of the ability of an atom to attract electrons to itself. So it's sort of like in a tug of war, electron tug of war, the higher the electronegativity, the stronger that atom pulls those electrons toward itself. The numbers are kind of arbitrary, but they're all based on a scale. Fluorine has the highest electronegativity of 4.0, and then they're measured against each other all the way down to 0.7. And again, the higher the number, the more the atom attracts electrons. Notice that the highest values tend to be in the upper right-hand corner of the periodic table. Fluorine's the highest, and then oxygen and chlorine are very high, nitrogen, bromine, and so forth. All right, so if we have a covalent bond that is made up of two atoms that have the same electronegativity. Now in this case, this is picture A. In this case, we happen to have two chlorine atoms. So naturally, because they each have the same electronegativity, they each have the same pull on electrons, they're going to be pulling those electrons evenly. So, and you can think of it as a tug of war. If both elements want the electrons the same amount as each other, they're going to share them evenly. This is called a nonpolar covalent bond, where bonding electrons are shared equally. If, however, one element has a higher electronegativity than the other, what's going to happen is it's going to pull harder on the electrons, move those electrons closer to itself, and by doing that, part of the atom becomes more negative. So if you see on part B, the chlorine has a much higher electronegativity than the hydrogen, which means the chlorine pulls harder on that shared pair. Because chlorine sort of has a bigger pull of those electrons, the chlorine itself is partially negative. Now, it's not a full negative charge where we had with the ionic compounds, but it's partially charged. And so those little symbols, it looks like a squiggly line. It's a Greek letter delta, lowercase delta, and delta negative means that it's partially negative, and the delta positive means it's partially positive. So the one that has the stronger pull on the electrons, that end of the molecule will be more negative. And so this is called a polar covalent bond. Here's some other examples. Again, because the electron cloud is pulled more toward the one with the higher electronegativity, then it becomes more negative. So just two more examples. An OH bond is a polar bond because the O is more negative than the H. A CH bond is considered nonpolar because it's a pretty even distribution of the negative charge. You can actually determine what the polarity of a bond is by subtracting the difference between the electronegativities. So if we look at the difference between them, we'll see how different they are from each other. To find the difference, you subtract the smaller one from the larger one because you always want a positive number. So you want to compare differences, but only if they're positive. And so then you compare the value to this sort of range. If the difference is less than 0.5, that means the two atoms are very similar to each other, so they pull pretty evenly to each other, and so we consider the bond to be nonpolar. So smaller than 0.5 is nonpolar. If the difference is equal to 0.5 or greater than 0.5, but less than 2.1, we consider it polar. There's a pretty large difference between the two atoms. The one with the higher number will have a stronger pull on the electrons. Now, actually, this is kind of a wide range totally that sort of picks up the last unit as well. If the difference is 2.1 or greater, that means the electronegativity is so different that in fact the one atom with the higher electronegativity is so much stronger it'll actually steal that electron away and become negative, leaving the other atom positive. And in that case we have an ionic bond from the last unit. So again, less than 0.5 is nonpolar. Between 0.5 and 2.1, including 0.5, is considered polar, and 2.1 or greater is considered ionic. So here are some examples. I've gone back to the chart a few pages ago where the values are given on the periodic table. So if we look up the electronegativities of oxygen and hydrogen, we subtract them, we get a difference of 1.4. So since that's greater than 0.5, this is a polar covalent bond. The oxygen is the partially negative because it's the higher number. Sometimes you'll see a polar bond written. You can see the arrow with the arrow pulling in the direction of the negative charge, and so the plus sign is sort of on the positive end, and then the arrow is on the negative end. If you look at the difference between carbon and hydrogen, 2.5 minus 2.1 is 0.4. We consider that nonpolar. So carbon and hydrogen really share electrons pretty evenly. Of course, if the bond is between two of the same elements, then the difference is always 0. So in this case, a carbon bonded to a carbon, 2.5 and 2.5, the difference is 0. So that is always a nonpolar covalent bond. Now the NH bond, the N is 3.0, the H is 2.1, the difference is 0.9. So this is a polar covalent bond, greater than 0.5. The nitrogen is more negative and the hydrogen is more positive. The nitrogen has the larger number. All right, looking at Mg and C, this one kind of works in the opposite. Mg is the smaller number, 1.2. Carbon is larger, 2.5. If you find the difference, it's 1.3, which we know is greater than 0.5, so that's a polar covalent bond. This time the carbon is the negative end and the magnesium is the positive end. And then finally, if we look at the NaCl, Na is 0.9, Cl is 3.0. The difference between them is 2.1. Clearly such a large difference that in fact the chlorine is so much larger than the sodium that it pulls the electron away from the sodium, making it a fully positive charge on the sodium and a fully negative charge on the chlorine. So no little partial squiggly deltas. All right, so most of the time, if there is a polar bond in a molecule, the molecule will be polar. So, we're looking at two different things. We're looking at a particular bond between two elements, trying to decide if that bond is polar or not. And now we're going to apply this to a whole molecule to see if the whole molecule is polar or not. So again, most of the time you have a polar bond, the molecule will be polar. So for example, an OH bond in water is polar, where the oxygen is more negative. And then we have two of those bonds, so they both pull toward the oxygen, meaning that overall the oxygen end is more negative and the hydrogen end is more positive. So water is also a polar molecule. It has polar bonds, and together those polar bonds make a polar molecule. However, there are just a few instances that the polar bonds interact in a way that cause them to cancel each other out, which we'll see on the next slide. So CO2 is one of those. So in this case, because the CO bond is polar, and notice on the CO2 molecule, the oxygen pulls to the right and the other oxygen pulls to the left. Well, because the molecule is a linear molecule, sort of like a tug of war, each oxygen is pulling the same amount but in opposite directions. So what happens is this molecule, they cancel each other out, and this molecule is considered nonpolar. So even though the molecule has polar bonds, we call that molecule nonpolar. Now comparing that to the oxygen, because of that bent shape, remember I said that that was going to be really important. Because of that bent shape, the oxygen pulling from one hydrogen and pulling from the other, these are called vectors, which are they're they pull each other, they have direction and intensity. So because it's pulling up and the other one's pulling up together, the oxygen has a negative charge. And so water, the two bonds don't cancel each other out, so water is considered a polar molecule. It has polar bonds and it's polar molecule. So how can you tell if a molecule is polar or not polar? Well, here's a little flow chart. You might find it a little bit confusing, but just follow the questions. The first thing, if you're looking at a molecule and you want to know, is this molecule polar or nonpolar? The first thing you want to do is ask yourself, well, are there any polar bonds in the molecule? So what you do is just pick a bond, look at it, decide if it's polar or nonpolar. If it's polar, then the answer is yes, and you move on. Well, if it's nonpolar and there are other kinds of bonds, then take a minute and look at the other kinds of bonds and just check to make sure that there are no polar bonds in the molecule. If there are no polar bonds in the molecule, then first of all, the molecule is not polar. You have to have a polar bond in order to have a polar molecule. So if there are no polar bonds in the molecule, you're done. It's not a polar molecule. But if you find a polar bond in the molecule, then you need to ask yourself one more question. Look at how many attachments there are, and these are the same attachments that we talked about when we were talking about the shapes of the molecule. If there are 3 attachments, are they all 3 identical? Are there 2 attachments or 2 electron clouds? Are they identical? Yes, then the molecule is not polar. If there are 2 and they're identical, if there are 3 and they're identical, or if there are 4 and they're identical, then what happens is they cancel each other out and the molecule is not polar. So, are there polar bonds? Yes. Are all the attachments identical? If the answer is yes, then they cancel each other out and the molecule is still not polar. However, if they're not all identical, then the molecule is polar. So if you have a polar bond, almost always the molecule is polar. It's just if there's a symmetry, if all the bonds are the same exact bonds, then they can cancel each other out. So let's look at a few examples. All right, so NH3. First of all, ask yourself, are there any polar bonds? Well, the only kind of bond we have is an NH bond, so let's check that out. Yes, nitrogen is 3.0, hydrogen is 2.1. If you subtract them, that's 0.9. So that is a polar bond. NH bond is polar. So now move on to the second question. Are all the attachments identical? Or when you think of attachments, think of electron clouds. Well, there are 4 electron clouds. The nitrogen has 3 bonds and 1 unshared pair. The unshared pair is not the same as a bond. So if there are 4 attachments but they're not identical, then they don't cancel each other out and the molecule is polar. So NH3 is a polar molecule. Now look at the next molecule, CCl4, carbon tetrachloride. Are there any polar bonds? Well, yes. The CCl bond, Cl is 3.0, C is 2.5, so subtract them, you get 0.5. They're just barely polar, but they are polar. So yes, there are polar bonds. Now, are all the attachments identical? Yes, because the carbon is, each bond is bonded to a chlorine. So CCl, CCl, all 4 are identical, which means they cancel each other out, and your overall molecule is not polar. How about CH4? Well, are there any polar bonds? Well, look up carbon, 2.5. Look up hydrogen, 2.1. The difference is 0.4. We said that that's nonpolar, so if there are no polar bonds, we're done. The molecule is nonpolar. Now let's look at CH3Cl. Now these are the same, we're looking at the same kinds of bonds, but here's an example of where there's different types of bonds. So are there any polar bonds? Yes, the CCl bond is polar. Now what I was saying before is, maybe you just pick a bond. So maybe the first bond you picked was the CH bond and you said it was nonpolar. Well, just double check all the other bonds first to make sure that there aren't any polar bonds before you answer that question. So the CH bond is not polar, but the CCl bond is polar. And so because they're not all identical, they don't cancel each other out, so the molecule is polar. Okay, let's just take a little brief detour and talk about how we can name covalent compounds. They're a little bit different than ionic compounds. The only ones we're going to worry about are binary covalent compounds, which means they only have two elements involved in the molecule. Two different types of elements. There's millions and millions of covalent compounds and millions of names, and some of them are very complicated. There's organic chemistry, which has a whole different naming system where you have to learn it. You have to take a whole year-long course to learn it. But the ones we're only going to focus on are these binary covalent compounds. So here's the pattern. It's very similar to ionic, except for what you'll see, one thing that's different. The pattern is always to name the least electronegative element first, which is usually the one that's listed first, and then the more electronegative element second, which pretty much anything you'll have will have the first element and the second element, and you just do them in order. You change the second element to the IDE ending, just like we did with the ionic compounds. However, the difference here is that, remember with the ionic compounds, because of the charges, they only paired in very particular ratios. So we didn't have to indicate how many of each there were because it was given in the elements themselves. So like magnesium and chlorine, Mg was a 2 plus, Cl was a -1. So we always have to have MgCl2. We just call it magnesium chloride because if you look up magnesium and chloride, you know that the ratio is 1 to 2. But it's not quite the same in covalent compounds because the ratios can vary. So, for example, you can have SO2, we name it like this, sulfur dioxide. So what we're doing is we're putting a prefix in to indicate how many of the elements are. You can see over in the right-hand side there is the Greek prefixes that we'll be using. If there's just one, we use mono, 2 is di, 3 is tri, tetra, penta, hexa, hepta, octa, nona, and deca. So again, going back to the top, SO2 is sulfur dioxide. The reason why we have to say dioxide, if you looked up sulfur and oxygen, they both tend to make negative charges. So they're not going to make an ionic bond. They're both nonmetals, so they're going to make a covalent bond. And here's the thing. Sometimes sulfur can also make a bond with 3 oxygens. In that case, you would have sulfur trioxide. So that's why we have to indicate how many there are, because there can be so many different variations and we have to indicate which one we have. Okay, now xenon and fluorine. So what would be the name? Xenon hexafluoride, because there are 6 fluorides. H2O, of course, that's water, but let's put it together with its official name. Well, there are 2 hydrogens, so that's dihydrogen. And there's only 1 oxygen, so we say monoxide. You kind of we kind of drop that O to make it easier to pronounce. So H2O is also called dihydrogen monoxide. Now, sometimes a 1 is not used. Sometimes it is used, especially if there's only one of the first element. We usually don't use the prefix mono. If you don't see a prefix, you assume it's 1. But sometimes if it comes later in the compound, we often will say mono just for emphasis. Now, officially, you don't have to. H2O could also be called dihydrogen oxide. and it would be assumed to be 1 if you don't see a number. But mono just sort of adds a little bit of emphasis. So what are some other examples? Well, we already talked about one, CO2, carbon dioxide. Now here we do add the emphasis. What about CO? That would be carbon monoxide. So we have to put in the prefix to indicate the number, and those are just for covalent compounds, which are made up of two nonmetals. All right, so now we have these molecules. We have some molecules that are polar. We have some molecules that are nonpolar. Now here comes sort of the really interesting part. These kind of things tell us important properties about the molecule itself, or the shape and the polarity of these molecules pretty much dictate how the molecule is going to act. So, unlike ionic compounds, molecules are neutral. So they're not really strong attractions between molecules the way they are between ionic compounds. But this doesn't mean that there are no interactions between molecules. There are actually 3 kinds of important, we call them intermolecular forces because it's between molecules, to hold molecules together. And the 3 we're going to look at are called dipole-dipole interactions, hydrogen bonding, and London dispersion forces. If there weren't any of these kind of interactions between molecules, we would have nothing in the liquid state at all. Everything would be in the gaseous state because there would be nothing holding molecules together. Now we're going to get much more into solids, liquids, and gases in another unit, but in order for a gas to become a liquid, the molecules have to get closer to each other, which means they have to be attracted to each other. So something to keep in mind for the future. All right, so let's talk about each kind of attraction. These aren't official bonds, but they are attractions between molecules. For a little bit of clarity, there's intermolecular. Inter means between. Intra means within. So if you're trying to think of the difference, if you talk about intramurals, that means just like sports within the same school. If you're talking about an interstate highway, you're talking about a highway that goes between the states. So we're talking about intermolecular forces. Actually, the intramolecular would be the bonds that we've already talked about, covalent bonds and ionic bonds. But these are intermolecular attractions between molecules. Okay, so dipole-dipole forces are actually very important forces. They are attractive forces between molecules that hold them together. Now, why are they attracted to each other? Well, remember that a dipole molecule, a molecule that is polar, will have a positive end and a negative end. So if you have a molecule that's got a positive end and a negative end, and then you bring another molecule along that's the same molecule, the positive end of one molecule will be attracted to the negative end of the other molecule. So even though they're not ionic, they're still partially charged and will be attracted to each other. So you can see in this picture that the positive hydrogen end is attracted to the negative chlorine end, and so they line themselves up and they sort of stick close together. And this is called a dipole-dipole force. Sometimes you'll just hear the word dipole force or dipolar force. So you don't actually have to say dipole-dipole, but sometimes you'll see both words because it is a dipole attracted to another dipole. Dipole just means 2 poles. That just means a molecule that has a positive end and a negative end. Okay, hydrogen bonding is actually a little bit of a misnomer because it's not a true bond. It is also an attraction, just like a polar attraction. However, it's given this name because it's a really strong interaction between molecules. It's really just like a dipole-dipole interaction, but it's considered stronger, and you have to there has to be some particular particular items that have to be satisfied. So particularly, hydrogen bonding has to be between an H. The H has to be attached to an O, N, or F. And then the H is also attracted to an O, N, or F. So if you look on the bottom left-hand side, you'll see the two water molecules. You'll see that the oxygen is partially negative, the hydrogen is partially positive. Well, then on the right-hand side, you've got another water molecule. So the hydrogen, which is positive, is attached to an oxygen, which is negative, but now you see that that hydrogen, see the dashed line, that hydrogen is attracted to an oxygen on a neighboring molecule. So it's very particular that it has to be a hydrogen attached to an O or an N or an F, and then attracted to another O, N, or F on another molecule or another part of a molecule. You can see the pictures. There's hydrogen bonding that happens between water. So a positive end of water is attracted to the negative end of water. Now, the reason why this is, so it's still dipole-dipole because it's still a positive end and a negative end, but we give it its own category because hydrogen being so small can get in really, really close to another molecule. And then the O, N, or F, remember those are the very highest electronegative elements that are on the periodic table. So these are the sort of the most polar bonds that you can have, an O, N, or F bonded to a hydrogen. And then the hydrogen being so small, it means that that attraction is a really tight interaction, very strong interaction. Hydrogen bonding is a hugely, hugely important force in the world. So, I mean, it's what makes water a liquid at room temperature. Water is a very unusual molecule. Because it's so small, if you follow patterns of molecules, and we'll talk a little bit more about this later, but water should be a gas at room temperature because it's such a small molecule. But because of these very strong hydrogen bonds, it is a liquid at room temperature. And of course, we couldn't have life without liquid water. And so without hydrogen bonds, we wouldn't have life. You can look over on the right-hand side. Hydrogen bonding is the key to many biological systems. So if you see here, now it doesn't, I said that the H has to be attached to an O, N, or F. And then attracted to an O, N, or F. It doesn't have to, they don't have to be the same. So if you look over on the right-hand side, that's DNA. These are the two strands of DNA being held together. An adenine and a thymine are held together by hydrogen bonds between an H on an N attracted to an O and an H on an N attracted to another N. The guanine and cytosine, same thing. You've got hydrogen bonds between the H's attached to N's and attracted to O's, or H's attached to N's and attracted to other N's. So it's these hydrogen bonds that hold many, many biological systems together. So it's a very important attraction. There's one more force, which is called a London dispersion force. And this happens with nonpolar molecules. So if you have a nonpolar molecule, it doesn't have a positive or negative end. It's just very neutral. And so you would think, well, they don't, then two nonpolar molecules shouldn't attract each other. Well, they actually do. They have a very weak attractive force, and it is called a London dispersion force. So what happens is if you have a molecule which is nonpolar, and you can see the pictures on the bottom, if the electrons are symmetrical, so they're kind of all over the place, then the molecule is not polar. But electrons are constantly moving, and it might just happen that at some instant in time, all the electrons might end up on one side of the molecule, like you see in the second picture, the middle atom. If that happens for that instant, the right-hand side is partially negative and the left-hand side is partially positive because all the electrons are pulled to one side. Now, it doesn't stay that way. It keeps moving, and so it's just a very short instant in time that this happens. But when it does happen, a neighboring atom, which you can see here, or molecule, either one, will be induced into a dipole. So because the one in the center has the negative end, it's going to push away the electrons on its neighbor, creating a dipole in its neighbor. Now, probably before the first one goes back to normal, the second one will appear and the first one will go back to normal. It's very, very quick, very light attractions that don't stay very long, very static. However, it's enough to hold these molecules together. Sort of, I like to describe it as sort of the wave. So the first person starts the wave and the next group does it right afterwards, but by the time the third group has it, the first one's done. And so it just keeps moving down the line. It's the same thing with a dispersion force. London, I think, just has to do with the person who discovered them. So, but London dispersion forces or dispersion forces. All right, now while we're talking about it, we'll talk about one other type of interaction, and that's the metallic bond. They're neither ionic or covalent. Basically, what a metallic bond is a bunch of nuclei, positive nuclei, with a bunch of electrons sort of flitting between all the different nuclei. The negative electrons can actually move between the positive charges between all of them and kind of keep moving, and that's what makes metals good conductors. So electrically, you use metals to conduct electricity because the electrons can move freely. That's all you need to know about metallic bonds. All right, so we have, let's include also our ionic bonds. So ionic bonds are very strong interactions between a metal and a nonmetal. Then we can have two metals that are held together by a metallic bond. And then we have our covalent bonds, which are molecules held together between two nonmetals. And then in addition to our covalent compounds, we also have intermolecular forces that hold molecules together. London dispersion forces, which are the weakest, that occur between nonpolar molecules. Dipole-dipole interactions are in the middle, and they happen between polar molecules. And then hydrogen bonding forces are the strongest category of dipole-dipole forces, and that happen between a H attached to an O N or F and another O N or F. So these are the strongest intermolecular attractions. They're not quite as strong as ionic attractions or covalent attractions or metallic attractions, but they are the strongest out of these three intermolecular forces. So we'll get more into this in the future, but covalent compounds, the properties and the characteristics of these compounds have a lot to do with what types of interactions they have between molecules. So high melting points and boiling points are true of ionic compounds because they have very strong attractions. Well, the same thing happens with covalent compounds. If you've got a covalent compound that has very strong hydrogen bonding, they're going to tend to have higher boiling points and higher melting points. If you have molecules that are nonpolar, and so we only have London dispersion forces between them, they're going to have lower melting points and lower boiling points compared to other things. So we're going to look at these properties a lot more in another unit, but just to kind of get you thinking about it. All right, so this is just a little summary, but now this is just going to tell us the difference between ionic compounds, which we talked about in last unit, and molecular compounds. So in ionic compounds, the smallest unit is called an ion. In the molecular compounds, the smallest unit is a molecule. Ionic compounds are usually a metal along with a nonmetal or a metal and a polyatomic ion. Molecular compounds are composed generally of two nonmetals. Ionic compounds are crystalline. We said that last time. They're very rigid. Molecular compounds can be gases, liquids, or low melting solids, and they're not very regular. Ionic compounds tend to have high melting points. Molecular compounds tend to have low melting points, ionic high boiling points, and molecular low boiling points. Of course, there's a lot of range in between. If you've got a hydrogen bond, it's going to be higher than something that is just London dispersion. But overall, molecular compounds are slower than ionic compounds. Ionic compounds conduct electricity when they're melted because of the charged particles, whereas molecular compounds do not. Many ionic compounds are water soluble, and we're going to talk a whole lot about that in another unit. It's because of the interaction between the ions and the water. A few molecular compounds are water soluble, except for water and some other things that are similar to water. Ionic compounds are not soluble in organic liquids, and many molecular compounds are soluble, although not all. So that's just kind of a generalization. All right, so that is the end of Unit 6. I hope you have enjoyed it.